So good morning. We have started with the force vibration and we have seen the total solution of the force vibration is depend upon two factors. One is the complementary function and other is the particular integral. So as if you're taking the complementary function, this is the equation which is equivalent to your underdamped free vibration case, which is equivalent for n is less than 1. And then for particular integral, we have done this particular analysis. And finally, we lead to the two equations, which is, so this is for particular integral. This is what the equation is, where you can see this is a cosine function, and this is the amplitude of the cosine function, which has been coming. If you merge it, then it will be looking like this, and then we have found out the value of A and B. And finally, you achieved at this particular response. If you see the response, the first is for the complementary function, which is looking like this, which is the exponentially decreasing harmonic function. And second is the cos lambda t minus theta into some amplitude. So which is nothing but it is the cosine function. If you merge these two, then the response will be this dark line, right? So initially you have the random vibration, and after that, this particular influence of random vibration will actually merge because of the damping, and then there is a single response. So up to certain time, this will be the governed by both the function, which is complementary and particular integral. But when you take the t tends to infinity, only the particular integral will govern this particular response. So that response we used to say is a steady state response. And combination of this particular response, you generally get, you can see the random or the transient response. We have also given the example of the car or any machine. When you start initially it will vibrate, you can say the randomly or transiently, and after few seconds the motor will be smoothened down. So this is nothing but this is the response. If you see the physically in all type of machine, in car or in vehicles, right? So generally when you start, you will feel such type of random vibration, and then it will be smoothened out. So only the particular integral will actually carry forward the vibration when the t tends to infinity. So with this explanation, let us go further. So as you said, this is t tends to infinity is a steady state vibration. And now, so if I write this particular formula in this way, like if I take the limit t tends to infinity x of t, then it is equal to what? That is nothing but it is the particular integral, what we have seen from this particular formula. So when the t tends to infinity, when I'm talking, then only this particular part is going to govern, which is nothing but the particular integral, right? So here I've written the xp of t, and the formula for xp of t is what we have derived is p by m cos lambda t minus theta upon under root of omega square minus lambda square whole square plus 2 eta omega lambda whole square. This is what the formula we have seen. Now based on this particular concept, I am trying to develop the relations for steady state displacement. Very, very important formula. Now when I am saying the particular integral or a steady state, exactly when the t tends to infinity, this particular integral will become the steady state one, right? So I can write in place of xp of t, I can write xs of t, where the s is nothing but which represents the steady state vibration case. So the same equation, but I am just changing this suffix. This s is denoting the steady state displacement of an vibration, particularly the force vibration, which is equivalent to your particular integral equation, which is nothing but this, which is p by m cos lambda t minus theta upon under root of this. Now what I am doing is I am dividing this particular equation from top and bottom with omega square. So this will be, then this equation will become p upon m omega square cos lambda t minus theta, and in under root this will become omega square divided by omega square is 1 minus lambda square upon omega square whole square plus 2 eta lambda upon omega whole square. When I am dividing omega square and top and bottom, then this particular formula will come. Now I'm defining one more frequency or one more definition. That definition is nothing but it is the ratio of operating or exciting frequency to the natural frequency of the vibrating system, right? So if you see, this is the, let me take a pointer. So I am talking about this particular relation. So I am denoting this particular ratio is a small r. This small r is the ratio of operating or exciting frequency, what we have said is a lambda, to the natural frequency of the vibration. Also, I'm trying to define this particular term, which is P upon m omega square. So if you see P upon m omega square, so this will become P upon m omega square. As you know, it is nothing but the under is equal to K by m. So the mm is going to be cancelled. So this will be the P by K. So if I take the P is the force, right? P is the force and K is the displacement of the vibrating system. Sorry, K is the stiffness of the vibrating system. Then force divided by the stiffness is nothing but your displacement. And that displacement is nothing but, I am supposed to say it is a XST. So this is nothing but it is your static displacement. Am I right? If your P upon K, if the P is the force, K is the stiffness, then this will be nothing but XST. This XST, what we say is, it is my static displacement. So with this explanation, I am going to put this 2 into this particular formula. So if you see P by omega square is been replaced with the P by K or XST. So you can see the P by m omega square has been replaced with the XST. It is nothing but it is a P by K, and P by K is nothing but X upon ST into cos lambda T minus theta. And this will be replaced by R. So 1 minus R square whole square plus in bracket 2 eta R whole square. So this formula will be like this. So this is now the new formula for steady state displacement. Now in this formula, if I'm taking the static displacement on this side, then this will become XST upon capital XST, right? So this is my dynamic displacement to the static displacement ratio is equal to 1 upon this formula, that is 1 upon under root of 1 minus R square whole square plus 2 eta R whole square into cosine term, which is cos lambda T minus theta. So basically this is the amplitude of this particular cosine term, right? Now, if one more definition I'm here putting is, that is the dynamic magnification factor, which is very, very important term when you are analyzing the vibration in terms of the amplitude magnification. So dynamic magnification is nothing but it is the ratio of amplitude between XST over static displacement. So basically this will give you the value. Suppose your amplitude in the case of static displacement is X, and now in the while you are actually system is going into the dynamic case, what is going to happen is some amplitude will magnify because of the dynamic system. So what is that particular multiplying factor or the dynamic magnification factor? How this particular magnitude is been actually magnifying when it comes from static displacement to the dynamic displacement? That is the value that has been given by this particular dynamic magnification factor. As it is saying, it is a dynamic, means it is a dynamic load. Magnification factor means it is how much it has been increasing. So that particular thing has been given by this particular thing, which is the amplitude of this ratio, which is the dynamic displacement to the static displacement. So if you see, the amplitude of this ratio is nothing but this for this case. So my DMF in this case is this, right? So this is my DMF value. So which is the amplitude of this, because this is the amplitude of cosine term. So I can take my DMF is equal to this. Okay. So DMF is nothing but it is the 1 upon under root of 1 minus r square whole square plus 2 eta r whole square. Now, once you find out the DMF, I would like to plot a curve between dynamic magnification factor on y-axis to the frequency ratio on x-axis, right? Okay. What is the use of this particular curve? This particular curve will be utilized for finding out or designing your machine foundation or the vibrating systems, right? So for each vibrating system, first you need to develop such type of graph, right? So whatever the equation we have taken, we have considered in this case, which is the forced vibration with the harmonic excitation. In such case, we can develop this particular dynamic magnification factor in this way. I will also take one more example later on for different other force vibrating system. Okay. Now let's see how this particular graph is going to be developed. So if you see in this DMF equation, how many variables are there? If you see, there is one variable is the eta, which is nothing but your damping ratio, that is 1. And second variable, that is the frequency ratio, right? So already I am taking the frequency ratio here. So what I am doing is, let's say in this particular graph, I will put some values here, 1, 2, 3, and so on, right? Up to this. Similarly, DMF also I am putting, you can say 1, 2, and I can plot this particular thing. Now for eta, I will take some of the variations. So first I will take the eta is equal to 0. If I will take the eta is equal to 0 in this equation, and if I take the r is equal to 0, because r I need to start from this point. So at this point, to draw this particular graph, I am taking r is equal to 0 and eta is also equal to 0. Put this equation. So 1 minus 0 whole square, so 1 plus 2 eta is 0. So this equation will be 0, right? So 1 upon 1 is 1. So for that, the value which has been coming, this is this. Am I right? Okay. Now if you take eta is non-zero, oh sorry, r is equal to, then you just come, you can say here, same value, eta is equal to 0, r is equal to 1. Now if you put r is equal to 1, then 1 minus 1 is 0, right? And here, because of eta is equal to 0, this equation is 0. So 1 minus 0, which will be infinity. So if you see this curve at point 1, when the frequency ratio is 1, this is going to be infinity stage. Can you see this? This is going to the infinity stage. It is not touching to this one point. So one line, it is not touching to the 1, but it is going, you can say, to the infinity. It tends to 1, but it is not be touching to the 1. Similarly, if you put r is equal to 2, r is equal to 3, then you will get, you can say, such type of curve. So if you plot it, you can say for this, then you will get this kind of a curve. It is also not touching, you can say, the x-axis. Okay. So this is for eta is equal to 0. Now, second, what I need to take is for eta is equal to non-zero, right? Eta is not equals to 0. So if I take eta is not equals to 0, again I need to start from here. So you can start from here. So at r is equal to 0 and eta is non-zero, let's say 0.1, right? What will be the value has been coming? So just put the value eta is equal to 0.1 and r is equal to 0. So if you put r is equal to 0, so 1 minus 0 is 1. Eta is non-zero, but still r is equal to 1. Sorry, r is equal to 0. So this term will be 0. So 1 upon 1 is 1. Again, it will be starting from 1. If you put eta is equal to 0.2, then also it will start from 1 only. So for all the eta, this value remain same, because my graph is going to start from 1 for this particular case. But for other cases, like if I put r is equal to 1, eta is equal to 0.1, then you will get, certain type of values. So this value slowly I'm going to plot it for eta is equal to 0.1, eta is equal to 0.2, eta is equal to 0.3. Then you will get this kind of a curve. So this is called as the graph between dynamic magnification factor to this. Now you know the definition of resonance. If you understand the resonance, what do you mean by the resonance condition, then you might have said that when your natural frequency of the system is equivalent to your operating frequency of the system, then the maximum amplitude is occurring, and that particular condition is being called as resonance. So if I take the ratio of this R, frequency ratio, which is a lambda over omega. So this is nothing but it is your operating frequency, this is your natural frequency. When these two become equal, then you will say that when this will become 1. So basically this, as per our crude definition, one may say that the lambda upon omega is equal to 1 at this particular point, the maximum amplitude is going to be happen. This is what is been representing from this curve. You can see when the frequency ratio is nearing to 1, you will see in all the graphs, you can say this value is having higher, right? Even in this case also, right? But this definition is not fully correct, because this lambda by omega in all the cases of damping, if you see, it is not exactly equal to 1, right? Some value before, you can say this value 1 means this maybe you can say 0.99, this may be 0.97, this may be 0.98. So very, very close to 1, but not equal to 1. So one may say that in crudely, you can say when the lambda by omega is equivalent to 1, then you can say the resonance condition will occur. Otherwise, you need to find out what is the exact location of this. So the question remains is how to find out the exact location where this peak is going to happen. So my question is, at what value of R your DMF is become maximum? At what value of R your DMF is become maximum, right? So what I'm doing is, to find out this, I will take, this is your DMF equation. If I'm take DMF upon dr is equal to 0, then I will get the value of R. So basically I will take the derivative with respect to the R. So if you take the derivative of this value will be this. You know how to do the derivation of this, where my R is not equals to 0. If you simplify this, then your value of R is going to become is R is equal to under root of 1 minus 2 into eta square. Now you put the value of different value of eta here, then you will get at what particular value of R your value is coming this. So you can take these three cases, eta is equal to 0.1, eta is equal to 0.2, eta is equal to 0.3, and see at what value of R your value is coming maximum. So if you find out something, you can say what I remember is something value will come at eta is equal to 0.1, this value is coming 0.997. Please calculate and do that. I'm just putting some random values. This will be coming, you can say some 983. This value will be coming, you can say 0.953 and so on. This all the values with eta is equal to 0.1, eta is equal to 0.2, eta is equal to 0.3. So if you see from this curve, and also if you put the R is equal to R in this equation, R here in this equation, then you will get what will be the value of DMF, maximum DMF. So if you put this value of R here, and if you simplify, then the value of maximum value of DMF, which will be coming this. So I can calculate what is the value of maximum DMF for different value of eta. So this values DMF max, and corresponding what is the value of R is been coming, right? So this way you can calculate these values. So if you see this particular graph, then you can actually visualize this is not approaching to 1. As my value of eta is increasing, my peak value is been shifting leftward side of the 1. right, for this case, right? So this is for 0.997, 0.998, 983, 0.995, whatever the value that you are calculating from those equations, right? So this way you can plot this particular DMF versus you can see the frequency ratio curve. So this is what the explanation about how to construct this DMF versus frequency ratio curve for forced vibration case. So we will keep up to this, then we will join for the next lecture. I'm able to take some few questions if you have on this.